Hello, my name is Valdemar, and I'm here today to talk about block format, the next generation graph native storage engine. I am the lead engineer on the block format project here at Neo4j. So let's start with the basics first. What is a database engine or a storage engine? So Wikipedia claims that a database engine is the underlying software component that a database management system uses to create, read, update, and delete data from a database. So this means that this is one of the lowest layers in a database. So let's take a look at what this is responsible for. So the domain of a storage engine is to lay out the data on disk, namely to decide which data to store, where to store it, how to store it, and how to access it. So how to find and search in the data that you just wrote. And the storage engine can have a few different prioritizations. So for example, you can prioritize read performance, meaning that you need to read data as fast as possible, even at the cost that writing it is slow, or maybe it takes up a lot of space on your hard drive. Or you can have a write prioritization, that you want to be able to write a lot of data, but reading it back is not that important. Or maybe your most important factor is the size on disk. You don't have a lot available, so you want to be able to write as much as possible without exploding in size. Or maybe robustness is the most important factor, that you want a lot of data redundancy in your format. Or maybe you just want a general purpose engine that does a trade-off of read writes, size, and robustness, which is exactly what we did with block format. So here on the right side, you can see a simplified view of the tech stack in Neo4j database. So on the top layer, we have the two surfaces, Cypher and Core API. Most of users use the Cypher to communicate with the database. And these, in turn, communicate with the database through transactions, so that everything you read or write to the database is transactional. A transaction, in turn, is communicating with the storage engine and with indexes if you have those. So if a transaction says create a node, the storage engine will decide, okay, this is where I put it. The storage engine then communicates with the hardware using the page cache, which is a memory map of files written to disk, and a transaction log to ensure crash resistance. So this is what the storage engine is responsible for. So with block format, our key goal was to create the next generation storage engine that can handle databases that are too large to fit in memory, and to design a storage engine with a high consistent performance over time as the database grows. And this is the main goal that we wanted to achieve with block format, mainly the high consistent performance. So we wanted something to be fast all the time. So let's take a look at the property graph model, because this is what a graph database is storing. So a graph has nodes, and nodes have, of course, a unique identifier. You need to be able to know which node is which. It has a collection of labels. So labels are just strings, and you can have no labels or you can have many labels. A node also has a collection of properties, and properties are simply key value objects. And then a node has a collection of relationships. It can have 0 relationships or a lot of them. So what is a relationship? It also has a unique identifier. It has a source node and a target node, so a relationship is directed. It has one type, works similar as the label to a node, but you can only have one, and it needs to be there. And then it can also have properties. So this type of data is what we need to be able to store. So if we take a historic look on the legacy store formats that have been used by Neo4j for a lot of years. We can see how that worked. So in the legacy formats, all the data was stored in different records in different files. So we had a node store where we stored all the nodes. We had a relationship store that stores all the relationships. We have a property store that stores all the properties. And then we use references to link these things together. So a node that has relationships has a reference to the relationship store. And then in order to handle the growing data, because you want more than one, we build something that we called relationship chains, so linked lists that bind them together. And the same way for properties. So a node that has properties will have a reference into the property store and then a linked list of properties. So if we take an example query, so here on the right, we'll have the disk, where each square is a page that we map into memory. So if we have a simple query here, we want to find the person nodes in this graph. So we will use the label lookup index to find the position of all these nodes on the disk, and then we read them and return the result. If we're interested in something slightly more specific, namely a specific person node that has a property name Bob, we'll have to go into the property store for each node and read the properties in order to find this one, and then do a filtering on them to return the results. So there is some extra reading to be done, of course. If we're then interested in the relationships to Bob that are of the type likes, we'll have to go into the relationship store and follow this linked list and find and filter on all the specific relationships we're looking for. So there's even more reading here. And then if we're looking for a specific relationship, namely the relationship between Bob and Alice, we'll have to go back to the nodes and read the properties again in order to find the Alice person. So as you can see here, there's a lot of reading in the legacy formats, and we are a lot of jumping around in different places. So what is wrong, or what could be done better than the legacy format? So data is spread out over multiple files in many different records. So when we read this data, we can have a lot of page faults, or at least a lot of accesses all over the memory. So this turns the query, makes it slow. And then we have the problem that performance degrades over time as data turns fragmented. So the more fragmented, the more data you have, the longer it's going to take to load and find all of it. And even more so, when the ratio of the stores, your database size to your available memory, when that ratio increases, meaning that there's a higher risk that you do page faults, have to bring the data from disk into memory, then your query becomes even slower. And then we have the additional problem that this is overly complex. So it was introduced a long time ago, and the reality has changed, and we've had to add features and solve problems in this format. So a lot of things has changed since it was introduced, and it's hard to do these changes in the legacy formats. So one of these things, for example, is that we need a different format to handle very large data sets. Some of you may have encountered the high limit format. So in order to support really large databases, we had to make a different solution that at the cost of performance. So now that we know how the legacy format works, let's take a look at what block format is doing instead, the new format. So block format, the key is that it leverages data co-location to ensure that graph local data is stored together on disk. And this enables faster access and much more efficient processing by minimizing data retrieval times. So the less we need to read, the faster things go. So in block format, the data is co-located. So we don't have a node store, a relationship store, and a property store. We have something first that we call the small store that stores small nodes that doesn't have a lot of data. And when the data doesn't fit there in the small store, we have something we call the dynamic store. And this is a store that has a dynamic record. So things that can be start out quite small and then grow as needed or shrink as needed. And then for those nodes that has a lot of data, we have something that we call the dense store, which is a tree structure to handle these specific nodes. So if we take a look at the same query, but for block format instead. So we have a match person, and here you can see that it's the same nodes that we find. We still have to read those nodes. And you can notice that these nodes are bigger on this. They take up a bigger portion of a page because they contain more data. If we're interested in finding specifically Bob, the properties are inlined on the node, so there is no extra reading involved here. We just go and deserialize the properties to find the one we're looking for. And then if we're interested in the relationships, Bob has a lot of relationships. He likes a lot of people, so all of these are stored in the dynamic records. We go there, we read once, and we find all the relationship in one place. So we don't have to chase all over the hard drive to find them. So if we're trying to find Alice from here, we just follow the references back to the nodes. And once again, the properties are inlined. So it's just to go to the node and read the property there. And this is how block format does the same thing. So let's go a little bit deeper on how this works, namely the data layout. So I mentioned here that we have something called the small store. And the idea here is that in many data sets, the majority of all nodes, so more than 50%, will fit in this layout only. So most nodes in most data sets are actually quite small. You have a node, you have maybe one or two labels, you have a few properties and then a few relationships. And if we can fit all data in one place, then as soon as you read the node, you have everything that belongs to this node. So we had basically a 128 byte static block. This is the node, and it's split into two parts. One part 64 byte node data, and the node data is labels and properties. And then we have 64 bytes of relationships data that belongs to this node. So we do dynamic packing here. So we cannot say exactly how much will fit. If you have more labels, you will fit fewer properties. And if you don't have any labels, you'll fit more properties. If you have small properties, you fit more than if you have large strings, for example. Same with the relationships. You fit a lot of relationships if the relationship doesn't have any properties. But if your relationship have a lot of properties, then of course you don't fit as many. But yeah, obviously it doesn't fit all the nodes in any given data set. So we need something more. And this is where the dynamic store comes in. So this grows and shrinks in 128 byte blocks. And we have two of these. So we have a dynamic node store and a dynamic relationship store. The dynamic node store is used when labels and or properties exceed the small store capacity. So they exceed the 64 bytes that we had. So you have more. Maybe you have 20, 30 properties. And this record can grow up to 8 kilobytes. So there's a lot of properties that we can fit in here. And then we have the same thing for the relationships. So when you don't fit the relationships in the 64 bytes, you need more space. We can have relationships up to 2 kilobytes. And this is when we use the dynamic relationship store. But not every node can fit relationships in only 2 kilobytes. There are some nodes that can have thousands of relationships, maybe 10,000, maybe 100,000, or maybe even 1 million relationships or more, and this doesn't fit. So we need something to solve that. And for this purpose, we have the dense store. So this is based on a multi-root generational B tree, and each node that is dense or has a dense type will have a separate root or a separate tree. So this is effectively a sorted map where we can go from node, type, direction to other node, and the value is the relationship properties, if there are any. So we can do quite efficient traversal. So even if a node has a million relationships, we can actually find things quite efficiently, or find ranges of things. So I want all the relationships of this type and this direction, and we can just go and read a section of the dense node. And we can note here that nodes that has relationships of different type, maybe it has 10,000 relationships of one type, but only 5 of a different type. Only the type that has a lot of relationships will end up in this store, whereas the type that has only few relationships will still be in the dynamic store. All right. So those are the key improvements that you can see. So we get faster queries. So when we do fewer disk and memory accesses, we significantly improve the read performance, and even write performance is improved because writing need to do a lot of reading, and updating fewer places is faster. It's also more memory efficient. So when your database doesn't fit in memory, then touching fewer pages is efficient because the other pages can then be busy serving other queries, and you don't stress your disk with I/O, so it can be busy doing other things and serving other queries. We get faster property access as well. So inlining the properties allows you to do that extra property filter in your query at basically no cost. So in the legacy formats, this could kill the performance of a query, but here it doesn't cost that much. And then we have a new thing that we call like the future proofing. So we designed block format specifically so that we can extend it in the future. We can add new things and performance improvements over time without requiring a complete store migration or rewrite of the store. This is something we can do in a rolling upgrade fashion. So database will still always be online for those that need. So how does this actually perform? Because this is the interesting part, I think. So here we have a chart over some aggregated data benchmarks when everything fits in memory. So this is when we have more memory available than the store is big. So we can see that the standard format is one of the legacy formats as a baseline, and we can see that block format is outperforming the legacy formats with almost 50% when everything is in memory. And then on the right-hand side here is we have block with cipher optimizations. It's almost twice as fast. So Cypher has been built and optimized for many, many years with the legacy formats in mind. And block format hasn't been around for so long. So over time, we can build a lot of improvements in Cypher that optimizes for block format as well. And we know that it can be up to 2 times faster because when we run on the core API, one of the other surfaces that you can interact with Neo4j, we see it's 2 times faster than the legacy formats. So with the proper optimizations, we'll close the gap with Cypher. So the future will bring very nice things here. So if we take a look at what happens when everything doesn't fit in memory. So on the far left here, we have everything fits in memory. So that's what we saw on the previous charts. And then when we start to reduce the available memory on the same thing, you can see there's a small drop in performance on the legacy format, but block format stays the same. And when only almost a third of the store is only in memory, then you can see that there's a significant drop in performance of the legacy format. Also, block format sees a cost here because reading from disk is always going to be slower than reading from memory. But we can note here that block format is still on 36% that fits in memory is faster than what the legacy format has on 100%. So this is exactly what we wanted to see. So let's wrap up with some quick facts about block format. So it took over 4 years to develop this. And there was a lot of engineering going into making this a reality. And we released this for everyone in February, so in Neo4j 5.17 this year. And then we made it the default format for new databases in July. So if you go in Aura and create a new database, this block format is what you will get. And you can control this, of course, with the db format equals block in the Neo4j conf. And that's how you control the format for new databases if you want to override it, or if you're on some version between 5.17 and 5.22. You can, of course, migrate existing databases that you've had laying around for a long time. Just use the Neo4j admin database migrate to format block. Or if you just want to check which format you have on a database, you can just do show databases yield name and store, and you will get the result using Cypher. And then we have, of course, official documentation that mentions some of the differences and key improvements, if you want to go there and have a look. And I think that was everything that I had. So if we have questions, please just ask.